The goal of this video is to come up with the form of the Jacobian matrix. So we've been talking about differentiability for vector value functions and multiple variables for a few videos now. And in our study of differentiation so far, we've covered this kind of grand definition of differentiability. The key idea is that if f is differentiable at p, then there is a linear transformation so that when we form this first order approximation out of this linear transformation, it really well approximates the behavior of our function near p, so well that this limit goes to 0. We've worked with this idea without actually saying what this linear transformation would have to look like. We know that to a linear transformation from Rn to Rm, there should be an associated m by n matrix. That's what we're going to find in this video. So we are going to actually say, well, if you have a function, here's how you compute the associated matrix. It's called the Jacobian matrix. And once you see it, you'll be able to do Jacobian matrices. We are going to start with a quick conversation about partial derivatives because those are key components to this matrix. Then I will say, take this limit. If we assume our function is differentiable, what would df at p have to be? So we'll take this expression kind of back out of it, the Jacobian matrix. We will wrap up after that with a quick example just to make sure we understand how to actually compute these with the form that we will derive. I'm going to go ahead and tell you the answer to what the Jacobian matrix looks like before the derivation. It's made up out of partial derivatives. So let's take a moment to just work through the notation with partial derivatives so that when we see it in our computation, we'll recognize it. The context here is imagine that f is a map from some open domain A, which is a subset of Rn, to Rm. In coordinates, what we can say is that f is a function of n inputs. So x1, x2 through xn. Speaking in generality, we will call the jth input x sub j. Then it takes us to Rm, which means that the output is an m tuple. Each of the coordinates of the output depends on the inputs. So what we can do is think of these as functions in their own right. We call them the coordinate functions or sometimes the component functions of f. So we have f1 through fm, and we will refer to just an arbitrary one as fi. For the coordinate functions, notice that each one is a map from A, so the same domain as f, to R. So coordinate functions are scalar valued, which means it makes sense to say that a coordinate function is increasing or decreasing or maybe flat. It doesn't necessarily make as much sense to say that about f if f is vector valued. So be careful because if you're just taking partial derivatives, it might be tempting to say, oh, the partial derivative of f with respect to x doesn't exactly make sense if f is vector valued, but you can take the partial derivative of all of the coordinate functions. They are all scalar valued, so it makes sense to say, well, what is the rate of change with respect to, say, an input? Okay, so be careful with your notation here, your subscripts. We have n inputs, m outputs. What we're going to do now is say, okay, imagine you take the ith output, so this ith coordinate function, f sub I. What if I want to measure how sensitive this function is with respect to the jth coordinate? So it's like, freeze all of the other coordinates so that it's a proper experiment. How does fi change relative to x sub j? That is exactly the idea of a partial derivative. I'm going to write it out with two different notations and two different limits, just to kind of summarize all of the ways to think about this. First notation will be the Leibniz notation. So we kind of fancy d, dfi dxj at p. That is Leibniz notation. I am partial to subscript notation. It doesn't look as good here where we've got subscripts on everything, but we'll have f sub I sub xj. So like the function sub the input. Looks better in multivariable calculus. At p. What we do is we say, start at p and just perturb in the jth coordinate. What that's going to look like, I'll address the limit in a second, but if I just perturb in the jth coordinate, it's like saying, okay, fix the first coordinate, the second coordinate, go to the jth coordinate, and add a little step, fixing all of the other coordinates. Here, h could be positive or negative. So this is just perturb it in either direction. How does it change? So take this and now subtract off. I'll just write f of p, meaning p1, p2, pj, pn, etc. So if I just adjust the input in one coordinate, I'm just trying to measure the sensitivity of f sub I. Sorry, subscripts here are very important. This is f sub I, this is f sub I. These are the coordinate functions. If I just perturb the jth coordinate, how does that affect this coordinate function? And then to compute the rate of change, we want to do the difference in our inputs that we're testing. So that would be pj plus h minus pj. Typically, we just write h. This is one way to write it with kind of coordinate expression. But the way that I like and what we will see in our computation is this is like start at p and perturb in the jth coordinate. So it's a more concise way to write this is to say start at p and add to it a little scaled version of the jth standard basis vector. So h, e, j. This will return you back these coordinates. So e sub j only has a 1 in the jth coordinate and 0 elsewhere, so it won't affect these, and then we're scaling that by h. How does this compare to where we started? And then get the ratio of that change to the change in the inputs. Again, be very careful with your subscripts. I'm doing this on purpose just to emphasize how important they are. No, I'm not. I make mistakes with my subscripts in this kind of language all the time, and it's just really try to catch yourself. So watch your subscripts, watch your coordinates, and then also watch your dimensions. I think I try to emphasize that as we study differentiation. So always know that when I write this down, f sub I, I'm looking at a scalar valued function, not the same thing as f, which could be vector valued. Okay, so we will see this type of expression emerge in just a moment when we come up with the form for the Jacobian matrix. Okay, I think this is a fun exercise. If we assume that f is differentiable at p, then that means that the limit we write down in our grand definition of differentiability is already known to exist and equal 0. So if we assume f is differentiable at p, I can say that 0 equals the limit as x approaches p of the norm of f of x minus f of p minus the linear transformation df at p acting on x minus p, which you can also think of as the associated matrix times the vector x minus p. That numerator all over the norm of x minus p. I know f to be differentiable, so this exists and goes to 0. Since A is an open domain, then P in A is an interior point. So let me just sketch a picture, which I will erase in just a moment. So P is not right on the edge. It has to be interior, which means that you can approach P through the domain in any direction. Like way over here, that would be bad. But when you take a limit, you imagine that you're very close. So for an interior point, I can approach P however I want to. And what we know is regardless of how you approach P in the domain, this limit exists and goes to 0. Therefore, we are going to say, let's not approach P haphazardly. Let's give our route to P a very specific form. In particular, let x equal P plus h times the jth standard basis vector, and you should recognize that from just a moment ago. If I alter my picture a bit, imagine this is R2, so this is either E1 or E2. That means that we are going to consider approaching P along the coordinate senses of direction. So this would be like P plus H E1. Here, H could be positive or negative. And this would be P plus HE2. This would represent that way of approaching P in the domain. Okay, then the limit as x approaches P now becomes a limit as h approaches 0. So we are converting our limit prefix here from one vector to another to a scalar going to 0. Okay, let's see what happens to this expression if we replace x with p plus hej. Well, first thing that happens is this becomes the limit as h goes to 0. Then f of x becomes f of p plus hej minus just plain old f of p minus df of p. X minus p, if you bring this to the other side, that's equivalent to hej. There's probably something you'd like to go ahead and do to that, but let's pause for just a moment. Keep going with the denominator. The norm of x minus p likewise becomes the norm of hej. Okay. I encourage you throughout this to distinguish between vectors and scalars. I dropped a vector hat there. I think otherwise we're good. All right. There's some simplification that we can do, and I think it's probably rewarding for you to pause and do some simplification on your own before I come back and continue the computation. Here, there's an immediate step to take. So looking at this and remembering that this is the action of a linear transformation, you probably want to go ahead and do something algebraically to this latter expression in the numerator. But there's actually even more. So there's like two conclusions that I would like to get to with this expression. And then in the denominator, similarly, you probably want to go ahead and simplify this. Just be a little bit careful as you do so. So watch your norm there. Let's come back in just a moment and I will continue this. All right, let's continue the computation. I imagine the first thing you did was bring this h in front because this is a linear transformation, so scalar pulls out. If I catch up with you, that will look like the limit as h goes to 0 of the norm of f of p plus h times the jth standard basis vector minus f of p minus h pulls out h times df at p acting on the jth standard basis vector. If you didn't take this last term further, just try to emphasize there's a little bit more to do because we have a matrix acting on a standard basis vector. Something special happens when you have that kind of matrix product. And then for the denominator, I want you to be careful because when I evaluate this norm here, it's a scalar times a unit vector. So you could think of this as the absolute value of h times the length of ej, which is 1. So my warning was don't write just h in the denominator, it's the absolute value of h. Okay. I don't know why sometimes I write not fancy h and sometimes I write fancy h. Not sure. Okay, let's keep going with this. The algebra I'm about to do, I think I'm going to stick with this line. So from this line, I'm going to now simplify further, and what I'm going to do is just make adjustments here instead of writing more and more because I'd like to try to finish this computation without erasing anything. So what I would like to recognize is that the denominator is now a scalar expression. It's just the absolute value of h. And in particular, it's kind of like having an absolute value scalar, so 1 over the absolute value of h times a vector norm. So what I'm looking at here is kind of like what I have factored here. Let me go backwards. Take the numerator and bring 1 over h inside. Okay, so as I said, I'm going to try to stick on this line. I'm going to take this h, bring it inside this norm, so that now I actually have one giant vector norm. Going the other direction, if I wanted to revert back to the form I just erased, you can think of this as a vector times the scalar 1 over h. What would it look like to pull that out? You would pull it out to 1 over the absolute value of h, and that would take us back. Okay, so now roll the numerator and denominator into one norm, which is safe once your denominator is just a plain old scalar. That's what we had. Then it's like, well, the next thing is we've got two terms here which pair up really nicely. We have h and h here. Seems like a smart thing to do is break this numerator up right here. So I'm going to divide each of these terms by h. Okay. And then let me do just a little bit more before we maybe write something new. And that is the obvious thing that you probably really want to do, and that's cancel out these h's. Okay, let's pause here so that you can make sure your final form matches this one. Well, it's not final, we're not done, but to get to this point, make sure you understand all of the algebra steps we did along the way. If you haven't recognized what's going on here, Think for a moment, what happens if you take a matrix and you multiply it by E1? So what does it look like? What happens when you multiply by E2? Because we can actually say something very specific for this term. The other thing I would like for you to do for a moment is think about the dimensions of all of the objects that we have inside of this vector norm. So what kind of elements are we working with here? And then I will come back and I think that we can reach our big conclusion with maybe just one more line. If you take a matrix and multiply it by E1, the first standard basis vector, you extract the first column from that matrix. If you multiply it by E2, you extract the second column. So df at P times the jth standard basis vector, this expression is actually the jth column of dfp. Notice that this second expression inside our norm has no h dependence. So this has no x dependence. It's just the matrix that we're trying to describe times a standard basis vector. Looking at this first expression, you might be tempted to say, hey, that's partial derivative. We just talked about that. But it's not quite, because f here is potentially vector valued if we're working in generality. So let's talk about dimensions for a second. This is an m by 1 column vector, so is this one. Dividing by h is just going to take that vector that you get in the numerator and scale it. So overall, this expression is m by 1. And likewise, this is the jth column of an m by n matrix. So it's m entries in this jth column, so that dimensionally we're doing something that makes sense. This is also m by 1. So the next thing for us to recognize is that I have a vector norm going to 0. So as the scalar h approaches 0, I'm saying this vector gets really close to this one so that in the limit, what we are taking the norm of is 0, so that our vector norm is 0. But if the norm is going to 0, then that means that the individual coordinates are going to 0. Maybe I'll make a note over here. I'm sure I'm going to end up erasing some stuff to give myself more room. Maybe not. But let's say some vector b goes to 0. Okay, so say b is changing, but b goes to 0, h dependence. Okay, v goes to 0 if and only if the size of its coordinates goes to 0. Maybe it's something called h goes to 0. So if this vector norm is going to 0, then each individual coordinate, when I break it up and look at the m coordinates here, each one of those is going to 0. And so let's now imagine that we go to the ith coordinate in these two vectors. Let's see, I think I'll just write a note here and then we probably fit one more line on to pass to the ith coordinates. Okay, what does that look like? Well, the limit is still the limit as h goes to 0. Sorry, my handwriting is going to deteriorate because I'm reaching down, but we are no longer going to write down a vector norm because now we're looking at the size of a scalar coordinate. So let me write absolute value. And then if I'm passing to the ith coordinate here, then that's like saying, what's the behavior of the ith coordinate function? That's what we called f sub I a moment ago. So in this numerator, I'm going to write f sub I at p plus h e j minus f sub I at p. So pass from this vector expression to this ith coordinate function. These are scalars now. Divide that by h. And then here, if I go to the ith entry in the jth column, that's like ith row, jth column. So to use standard matrix indexing, I'm going to say it's the ij component, the ijth component of this matrix. And this likewise goes to 0. Okay. We are now at the conclusion, but let me pause for just a moment if you'd like to think about this step, and then I will come back and kind of summarize. All right, just want to make sure that these indices are clear. This is ith. This is okay. I said my handwriting was going to go downhill, and it did. All right. This is just a number. It's the ijth entry in this matrix. So this has no h dependence. As h goes to 0, then I want to say that this is the partial derivative in just a moment, but it's not actually clear when we started this that the partial derivatives existed. Maybe I should have pointed that out. So if this exists in the limit as h goes to 0, then it is going to the partial derivative of the ith coordinate function fi with respect to the jth input, so x sub j. Now we can conclude really two things at the same time. One, that partial derivative does exist, and two, it's the ijth coordinate of this Jacobian matrix, so this associated linear transformation. The reason why I can say that is if this limit exists and goes to 0, and this expression has nothing to do with this one, then the fact that I'm taking the absolute value of something that goes to 0 means that this has to exist in the limit and equal that. Okay, so let me just write that a little bit up. So this implies that this number, which is the ijth entry of our associated matrix, equals the limit of this as h goes to 0. That's the only way this expression could go to 0. So f sub I p plus h ej minus f of p all over h. Oh, sorry, I. That's very important there. Don't forget, these are coordinate functions. Okay. So it's really two conclusions at the same time. What is the ijth coordinate of that matrix? And also the partial derivatives exist. That might have seemed obvious to you, but actually it isn't. So if we're just talking about differentiability and we haven't really gotten down into the coordinates yet, and I just say for this function, there exists an associated linear transformation, I haven't really connected it to the idea of the existence of partial derivatives. Now we're saying the partial derivatives of all of the coordinate functions with respect to each input exist, and together they form the coordinates of the Jacobian matrix. I'm going to write this down in more detail in just a moment, so I will erase all of this and we will kind of take a big picture view of this. We will also work through an example. Before I do that, I want to mention one more thing, which is that you cannot go the other way. We will talk about this, but let me go ahead and drop it into this discussion. The existence of the partial derivatives. In other words, your ability to compute partial derivatives and then plug them into the matrix to form what looks like an associated linear transformation is not the same thing as differentiability. So differentiability implies this is true, but being able to do this computation does not tell you that your function is actually differentiable. I'm not going to take that idea further in this lesson because we will have examples. We'll have lots of examples of this. So I just want to say that this is a one direction thing. Differentiability implies existence of partial derivatives. Converse is not true. Okay, so let me kind of erase all of this, and then I just want to write this out so that it really looks like a matrix. I want to make a couple remarks about sort of notation and vocabulary, and then we will have just a very quick example of a nice function. We will just write down its Jacobian matrix to make sure we're all on the same page. All I want to do right now is just gather all our thoughts together and put down an actual matrix, and then we will look at a specific example with an actual function. Okay, so what does this equality tell us? Well, if we have a function f differentiable at p with our usual assumptions, then the matrix associated to the linear transformation that we talk about in the grand definition of differentiability, the associated matrix has coordinates where when we go along the first row, those are going to be the partial derivatives of the first coordinate function of f with respect to all of the inputs. So I will use Leibniz notation here, and I will use subscript notation for our example. In Leibniz notation, that would be df1, dx1, and then df1, dx2, all the way through, dfm, dxn. And then we can just fill in the other rows. It's very easy to get turned around with your coordinates, so just do it slowly. Second row will be, and I just did it, so just to demonstrate, it's easy to get turned around. df2, dx1, df2, dx2, all the way through, df2. Oh, see, I got turned around here. Sorry, if you were really surprised I wrote this, it's because it wasn't correct. There, that's better. All right, df2 dxn. I have a better way to think about it in just a moment so that you don't have to do all of these little subscripts. Okay, then we continue down like this until finally we get to the mth coordinate function, which is dfm dx1 dfm dx2 all the way through dfm dxn. Okay, I think it's worth double checking everything. So to form the rows, grab each coordinate function one at a time. So df1, 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 and then x1, x2 through xn. Okay, that looks right. Second row consists of the partial derivatives for the second coordinate function. So f2, 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 okay, that checks out. And then with respect to each input, so x1, x2 through xn. And then the mth row of our m by n matrix is fm, 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 those partial derivatives with respect to x1, x2 through xn. Okay, I don't think I have any mistakes left. This matrix, as I just pointed out, it's m by n. It just has to be, so you can check out that that makes sense. I want to point out something notationally here. I'm kind of a stickler for both terminology out loud and notation. That is, here I'm saying the Jacobian matrix centered at P. So this is a linear transformation associated to our function when we're talking about differentiability at the point P. Here I've just written general partial derivatives, which is often how you compute this, is you start taking partial derivatives and then you plug in. So what you can do is like a giant evaluation bar and then say we're plugging in P. Okay. So maybe being a little bit pedantic, but basically each of these partial derivatives needs to be evaluated at this particular input. So that at the end of the day, if I'm talking about the Jacobian matrix for a function at a point, this should be a matrix of numbers. And then the other remark I want to make before we actually compute such a matrix for a very nice function is that if you look at each row, it might remind you of something from, say, a study of multivariable calculus. So here I have f1 is a scalar valued function, and I've computed all of its partial derivatives. Same thing here. It's like I froze a function, and then I just computed its partial derivatives. What I'm hoping that you're thinking about right now is the gradient of a scalar valued function. So I'm going to start to write something, and then I'm going to fix it. So if you know what I should be writing, just wait one moment. I will write it correctly. So if you want to write this matrix in a little bit more condensed way, what you can say is the coordinates of this row look like the gradient of the first coordinate function evaluated at P. However, let me fix this. For a scalar valued function, the gradient, when you form the gradient vector, it's a vector where all of the coordinates are the respective partial derivatives of that scalar valued function. It's a vector. So the gradient of f1 is an n by 1 vector. It should be written as a column. Here it's a row. So you must write this with a transpose. Okay, likewise, this is gradient of 2. Ugh, so many subscripts. The gradient of f2 evaluated at P, but converted into a row all the way through the gradient of fm evaluated at P turned into a row. Okay, so this is our famous Jacobian matrix. We are just about done with this lesson, but what I'd like to do is just take a nice function. I'm not going to prove it's differentiable. It's made out of really nice pieces. We will just take as fact that it's differentiable, and I will just compute its Jacobian matrix for you, I believe probably at the origin. Now that we know the form of a Jacobian matrix in general, let's just make sure we can do it for a specific example. So consider here this function f of x, y, and z equals e to the 3x plus yz, 4y plus cosine of y plus z. It's always a good idea to track dimensions. So I encourage you just to take a moment and think about what kind of function f is and what the shape of the Jacobian matrix should be. So f is a map on 3 variables, sending us to 2 coordinate functions. So here f1 is e to the 3x plus yz. That's our first coordinate function that we were working with in generality. And f2 is the other one, 4y plus cosine y plus z. So this is a vector-valued function of multiple variables. Don't want to get too off topic, but if this was r, we would say it's a scalar-valued function of multiple variables. So we know that df at the origin should be 2 by 3. All right, so let's write down that matrix. It's going to have 2 rows and 3 columns. We know exactly what we need to do. Differentiate the first coordinate function with respect to x, y, and z. So differentiation with respect to x gives us 3 e to the 3x plus 0. Differentiation with respect to y gives us z, and with respect to z gives us y. Moving down to the second row, there's no x dependence. So the first term in the second row is 0. And then we will have 4 minus sine of y plus z, and just minus sine of y plus z. I don't love what I've written right here, and let me explain why. This is supposed to be a matrix of numbers. So here I'm evaluating my Jacobian at a specific point in the domain. So whenever you set up the limit in our definition of differentiability, that matrix anchored at some point should be a matrix of numbers. Here I've got a matrix of functions of x, y, and z. That's why I tried to emphasize a moment ago that you can drop an evaluation bar and say, I mean all of this when x, y, and z are 0, 0, 0. Okay, and this is pretty common because when you're doing partial derivatives, it's not always a good idea to take the derivatives and plug in at the same time to go straight to numbers. So I like just writing down my partial derivatives and then evaluating. But at the same time, you always want to make sure you have proper equality. So matrix of numbers, just kind of in disguise. If I plug in 0, 0, 0, I will get 3, 0, 0. And down here, I will get 0, 4, 0. 2 by 3 as expected. We are done with this example, but at the risk of saying too much, just want to say that being able to write this down. So the existence of partial derivatives and the ability to put your partial derivatives together and say, hey, here's a matrix, is not the same thing as differentiability. Being able to write down a Jacobian matrix suggests your function might be differentiable, but it's not enough. So existence of partial derivatives is not equivalent to differentiability. This function, it's probably not surprising, it is differentiable because it's made out of such nice pieces. So there's nothing about this function that's going to be problematic. However, we have a lot to talk about with differentiability in upcoming videos. In particular, we will look at examples of functions where I can write down a Jacobian matrix. You know, the partial derivatives, they exist, but not only is the function not differentiable, it won't even be continuous. So be careful that you don't rely on your ability to write this matrix down as a way of assessing differentiability. It's a little bit different. If I, at this moment in our study, if I wanted to prove this function was differentiable, I would just take this and the function and plug it all into that definition, and then I would need to take the limit. Again, here it's silly because this function is so nice, but in general, that's the idea, is this gives you a candidate for the associated linear transformation, but it doesn't tell you that the associated linear transformation is good enough to make the limit equal to 0. Okay, I should probably stop there, otherwise I'll just keep going, and we have so much more to talk about. Thank you for your attention.